Hello and welcome. In this video, we will build and evaluate a convolutional neural network model for handwritten digit recognition using PyTorch. Let's begin by importing the required libraries. PyTorch and Torch Vision handle deep learning on datasets, while PAL and Matplot libraries are used for loading and visualizing images. Here, we define the CNN architecture. The network consists of two main convolutional blocks. The first block has two convolutional layers followed by RELU activation, max pooling and dropout. The second block repeats the same structure with more features channels. The layers help the network learn important shapes and patterns from digits. Finally, the output is flattened and passed through fully connected layers to classify digits from 0 to 9. Now we prepare the data set. The training and testing images are stored in folders, one folder for each digit. We apply transformations to every image, including converting to grayscale resizing to 288 by 288 pixels, converting to tensors, and normalizing. This ensures all images and have a consistent format before being fed to model. We then create data loaders for training and testing. Next, we move on to the most crucial part of the project, the training model. During the training phase, the neural network takes the input images of handwritten digits and tries to predict their corresponding labels. Each prediction is then compared with the actual labels, and the difference between them is measured using a loss function. This loss value helps the model understand how far it predicts from the correct answers. Based on this, the model adjusts its internal parameters called weights using a process known as backpropagation. For optimization, we use the Adam optimizer with a learning rate of 0.001, which ensures that the model learns efficiently without overshooting the optimal values. The training process is repeated over several epochs, meaning the entire dataset is passed through the model multiple times. As the epochs progress, you can observe the loss gradually decreasing, while clearly indicates that the model is learning meaningful patterns and improving its accuracy in recognition handwritten digits. Once the training is started and completed, the next important step is evaluating the model's performance using the test dataset. The test set contains handwritten digit images that the model has never seen before. This helps us measure how well our network can generalize to new data. We feed these test images into the model, and for each image it predicts a digit between 0 to 9. The predicted output are then compared to the actual labels, and we count how many predictions are correct. From the results, we calculate the overall accuracy score of the model. A high accuracy value indicates that the model has successfully learned meaningful patterns from the training data and is capable of recognizing new handwritten digits accurately, not just memorizing what it has already seen. Next, we get into the testing with a custom image. After confirmation that our model performs well on the test data, we take it a step further by testing it on a custom image, one that is not part of the dataset. We start by loading the custom image and applying the same pre-processing steps used during training. This includes resizing the image to the required dimensions, converting it to grayscale, and normalizing the pixel values so that data is consistent with what the model has already learned. Once pre-processing is complete, we pass the image through our trained CNN model. The model processes the image through its layers and finally predicts the digit it recognizes. To make the results more interactive and visual, we display both the input image and predicted output together. This kind of testing is extremely useful for real world demonstrations, helping us validate how the model performs on practical handwritten inputs, just like a real user might provide. After successful testing, the final step is to save the trained model. Saving the model allows us to store all the learned weights and configurations so that we can reuse it anytime without the need of retrain from scratch. In PyTorch, we can easily save the model using functions like torch save and later reload it using torch load. This process ensures that the effort spent during training is preserved and can be leveraged in future applications. By saving the model, we make it ready for deployment in various practical scenarios such as automated digit recognition systems regarding handwritten user inputs on digital forms, or even for further academic research and experiments. This steps forward our trained model from a simple experiment into a reusable AI component that can be integrated into larger systems or real world applications. Thank you for watching this detailed demonstration. In this project, we successfully built, trained, tested, and saved a convolutional neural network model designed to recognize handwritten digits using PyTorch. Through the process, we started from the very basics, importing and understanding the MNIST dataset, performing data preprocessing and structuring. The neural network architecture, we then trained the model, observed how long the loss gradually decreased, and evaluated its performance of unseen test data. The model achieved a strong accuracy, showing that it can generalize efficiently to new learning samples. We also tested it in custom images, which helped us visualize how the model performs in real world situations. Finally, by saving the trained model, we made it ready for reuse and deployment in various applications. Thank you for watching.